Hi everybody, welcome back. So in today's session, we are going to start off with coordination compounds. See, coordination compounds is literally a marks machine chapter. Whatever your focus of examination is, CSIR-NET, GATE, JAM, TIFR, whatever it is. Okay, so today we are starting with one of the most scoring and most important chapters of inorganic chemistry, coordination compounds. So this is one among the pillars of inorganic chemistry. You will get a lot of questions from here. Direct theory-based questions, structure-based questions, isomerism, CFT, MOT, whatnot, a lot of them. So easily you will get 8 to 10 marks from here if you learn this chapter. Okay, so we'll be covering everything in depth, from the basics to previous year questions to even the toughest and the advanced problems. So if you master this chapter, your inorganic score will jump instantly. So let's start. Please write down the heading. The first heading is ligands. We'll learn about ligands in detail today. Let's start. So I'm going to start off with a certain sets of coordination compounds. Chapter heading, coordination compounds. Okay, so one, let's say, just observe, okay? You can write it along also. NH3, 3 times Cl3. This is a coordination compound. So if you can see anything which is put inside the square bracket, this square bracket is called the coordination sphere. The square bracket, and you put something inside. So whatever is inside the square bracket, you call it the coordination sphere. So if we can see, the coordination sphere is not charged over here, and this is a neutral coordination compound. This is neutral. Okay, let's take another one. AgNH3 2 times Cl, let's say. So here, if you can see, there is a coordination sphere. You can see something is written inside the square bracket. And outside, there is Cl. There is chloride. So how will chloride exist? This will exist as Cl minus, and this will exist as AgNH3 twice plus. Correct? So the coordination sphere over here is positively charged. If so, you call that complex a cationic complex. You call it a cationic complex, right? Correct? Now, similarly, if there are cationic complexes, there will be anionic complexes also. For example, let's say K3FeCN 6 times. Example. So how does this exist? Potassium exists as 3K plus. Correct? Each potassium carries a positive charge and the coordination sphere carries a negative charge. So if it carries a negative charge, the coordination complex, the sphere carries a negative charge, and hence it's called the anionic complex. So the complexes can be neutral, carrying no charge, cationic, carrying positive charge, or anionic, carrying negative charge. Coordination compounds will exist like this. Okay, now the basic definition of a coordination compound is the moment you put these coordination compounds into water, they do not lose its identity. Okay, please note it down. Coordination compounds. Coordination compounds do not lose its identity in aqueous solutions. Okay, it does not lose its identity in aqueous solution. So what do you mean by that? Well, let's take any example. Let's take potassium ferricyanide. This is the complex. Okay, so the moment you put this in water, The way it will dissociate is the potassium ions will move freely plus the coordination complex, which is, if this is 3 plus, one potassium is plus, there are 3 potassium. So to neutralize the overall charge, this is going to be 3 minus, 3 plus and 3 minus. This is how it is going to exist. I hope you get it. It won't exist like there will be 3 potassium. This is there. And then 6 cyanide, that will come out. And then iron in plus 3. No, this is wrong. So if you can see, the ions which are present inside the coordination sphere won't dissociate in water. That will remain intact. So whatever is there inside the coordination sphere, that will remain intact. I hope that is clear. Okay, so it does not lose its identity. Let me see if this is being recorded, please. Yes. Okay, so we understood the basic definition. Now, the way the coordination compounds are written, if you can see, there is a central metal in all the case. There is a central metal. And surrounding these central metals, there are something called ligands. So I'm representing it by L. M is the metal, L is the ligand. Ligand can be N in number. It can be 1 ligand, 2 ligand, 3 ligands. Okay, so that is the number of ligands which are attached. And this is put inside a coordination sphere. Correct. And here there can be an ion. What kind of ions does come over here? So you can have cations over here. In certain cases, you can have anions over here. And we already learned that the charge of the coordination sphere can be positive, 0 or negative. We learned that much. Correct. So coordination sphere is whatever is written inside the brackets. We learned that these ions, it could be cation or it could be anion. Both won't be there. Okay. Either cation or anion would be there. Those are called the counter ions. Counter ions. Correct? You saw now, this is 3 minus. So the counter ions will be making a total charge of 3 plus. So these are called the counter ions. This is the metal, of course. And the metals are attached to the ligands. Ligands through a bond which is called coordinate bond. What do you mean by coordinate bond? Let's try to understand. Okay, let's say you have A with 1 electron, B with 1 electron, and both of these A and B decide to share them. If they decide to share them equally, each one of them is giving 1 electron. This is a covalent bond. This is a covalent bond. Now, what did I say? Metals are attached to the ligands through coordinate bond, not covalent, coordinate. What is coordinate? Coordinate means, let's say you have a metal, there is a ligand. Here also they share. They share the electrons, but it's not one each. See, here this electron belongs to A, this electron belongs to B. Each of the atoms has its own contribution and they form a bond. Here it's not like that. The ligand will possess the 2 electrons. Ligand will possess the 2 electrons and it is ready to share the 2 electrons with the metal. So this is also sharing, this is also sharing, but the difference is the way the electrons are shared. In covalent bond, each of the members, whoever is forming the bond, will give 1 electron each. But in a coordinate bond, one of the atom will give 2 electrons and the other won't give anything, but they'll share the 2. This is a coordinate bond. Okay, I hope you understand. So ligands are functionally those who are capable of giving that electron. What are the examples? NH3. N has got a lone pair of electrons. These lone pair of electrons can be given to some metal to form a coordinate bond. Correct? It makes sense, right? So let's say H2O. So here there are two lone pairs of electrons. So these lone pairs of electrons can be given to some metal to form a coordinate bond. Okay, so I hope you understand what is meant by a ligand. So ligand is someone who is capable of forming a coordinate bond. So if they have to form a coordinate bond, they have to give a lone pair of electrons. Now, very important. It's very important to understand that, let's say Cl, chlorine. Chlorine has basically 1, 2, 3, 4, 5 electrons around it. So this is chlorine. Chlorine, students understand that it cannot act as a ligand. Chlorine is not a ligand. You can see it has got two lone pairs of electron and one electron. Total 5 electrons total, but still it cannot act as a ligand. Why? To act as a ligand, its octet should be complete. Chlorine is not a ligand, chloride. That is already 5 electrons are there. Then it accepts one more electron. It accepts one more electron and it becomes Cl minus. So now it is chloride. So when it attains one electron, you no longer call it chlorine, you call it chloride. Chloride is a ligand. It has three lone pairs of electrons and that can act as a good ligand. This chlorine cannot. I hope you understand. So for anybody to act as a ligand, its octet should be complete. For example, in the earlier case, NH3. Let me split it up. You can see, right? 2 here, 2 here, 2 here, 6 from NH bonds plus 2, 8. 2 here, 2 here, 4 from bonds, 4 from lone pairs, 8. So it should always be 8 around whoever is donating the pair of electrons to form the coordinate bond. Okay. Now we said that coordinate bond is where you give the electrons. Where do they give the electrons? They give the electrons to the metal. So if you take some examples, CO, random examples, okay, and just NH3, let's say, and you have Cl, it can also donate, correct? And let's say water. Oxygen is the donor, correct? Water. So if we can see, lone pairs on nitrogen is donating, lone pairs on chloride is donating, lone pairs on water is donating. So you can either show it like this or coordinate bond can be shown like this as well, from the ligand to the metal. Now, where does these electrons go to? Okay, the electrons are taken up by the empty d orbitals. Empty d orbitals of the metal. Electrons are taken up by the empty d orbitals of the metal. So there are a lot of electron density being transferred to the metal. And where does it go to? It goes to the empty d orbitals of the metals. So you can see that most commonly, not always, most commonly, the metals that are present over here are transition metals. Transition means d block elements. Okay. Most commonly, they are d block elements. Okay, so this is understood. So today we are going to learn about ligands. How do you name them? What are the different types of ligands? You have to know everything. So let's start with the first type of ligand that is called monodentate. Monodentate ligands. Monodentate ligands. Mono means one. Okay, monodentate ligands are those which can donate lone pair of electrons from a single atom. From a single atom. For example, NH3. NH3, if you see, nitrogen is the donor atom. There is only one donor, nitrogen. Nitrogen is a donor. So if you have only one donor atom who is capable of, transferring the electron density to form the coordinate bond, that is called a monodentate ligand. Numerous examples. For example, NH3, H2O, these are all neutral. That means by default, their octet is complete of the donor. Oxygen is a donor. Correct? These are some of the examples of neutral ligands. Okay, there are more. There are more. You can take DMSO, DMSOS, dimethyl sulfoxide. Dimethyl sulfoxide. Correct? So you can see two here, two here, two here, two here. 1, 2, 3, 4, 5, 6, 7, 8. Octet is complete of sulfur. Then oxygen has got 4 from this bond, 2 here and 2 here. So this oxygen can donate. This is a neutral ligand, no charge, DMSO. Correct? Then you can have nitrogen. Okay, there are 2 donor atoms, but at a time only one will act. At a time, only one of the nitrogen will donate. Okay, so this is a monodentate ligand. I hope you understand. Carbon monoxide and NO, very important. Very important. NO, CO. Always remember, in NO, nitrogen is the donor. Oxygen's electronegativity is higher. As a result, nitrogen will be the donor. In CO, again, oxygen's electronegativity is higher, so C is the donor. Okay, so these are some of the neutral ligands that you can consider. Ligands can be also charged. We said about the coordination sphere, which can be neutral, anionic, or cationic. Ligands can also be charged. Why would they be charged? To gain the complete octet. What are the examples? Some of the examples are, so these are all neutral. These are all examples of neutral monodentate ligands. Correct. There are charged ligands also. Cl minus completes its octet when it gains one charge. I minus, Br minus, OH minus. Correct. O2 minus, N3 minus, NH2 minus, NH2 minus. These are all examples of ligands which are charged and monodentate. H minus, hydride. S2 minus, numerous. Okay, so these are SCN minus. These are all cases where they are negatively charged and at the same time they can donate their lone pair of electrons from a single atom. Okay, chloride, iodide, bromide, hydroxide, oxide, nitride. I hope you're getting it. Okay, here N is a donor, here also N is a donor, here oxygen is a donor, H is the donor, S is the donor. Here both S and N can act as a donor. At a time, only one will act. We'll talk about them in detail, but then at a time, only one will act as the donor. And these are all examples of monodentate anionic ligands. These are anionic because it carries a charge. Correct. Similarly, there is cationic also, NO plus. Cationic ligands. So these are some of the examples of neutral, charged, and anionic. So ligands can also be charged or neutral. And they form coordinate bonds with the metal. How do they form the coordinate bond? They give one lone pair of electrons. A pair means 2 electrons through coordinate bond. Okay. Now this ligand is of utmost importance, NO. NO can exist in 2 states, NO plus and NO minus. Both of these are possible. Very important. There have been a lot of PYQs from these 2 ligands. NO plus is also possible. NO minus is also possible. Let me take some time and explain that in detail. If you have some metal, Okay, you have got some metal. And let's say you take NO. So NO, N double bond O. Correct? You have one lone pair of electron. You have one electron over here. So 1, 2, 3, 4, 5, 6, 7. This is how it is. Correct? Nitrogen has got 3 valence electrons. This is how it looks. And oxygen has got 4 electrons like this. This is how you draw the diagram of NO. Now you can see if this NO has to act as a ligand, as the donor atom. If this has to act as a donor atom, its octet is not complete. 1, 2, 3, 4, 5, 6, 7. It has to complete the octet. Correct? It has to complete the octet. So in order to complete the octet, one electron from the nitrogen will be given to the metal first. What will happen? Metal will gain one electron and will become M minus. Okay. And nitrogen double bond O, 2 electrons were here. 2 plus 2, 4 electrons here. It has given one electron and now it will carry one positive charge. This is the scenario. Now, immediately when this sees a positive charge over here, this lone pair of electrons will transfer and form a triple bond over here to balance this. Now, what will happen? After this, there is a positive charge over here. Electron transfer happens. As a result, it becomes N triple bond O. This positive charge is now neutralized. 2 lone pairs already present. 1 lone pair of the oxygen is gone to make the triple bond. So this becomes positive like this. This is NO ligand with a triple bond. Okay, now this lone pair of electrons from nitrogen will form a coordinate bond with the metal, which is in M minus. So did you understand? First, one electron went to the metal, one electron went to the metal, and then after that, what has happened? NO has become NO plus, and NO plus after the formation of this triple bond will give the lone pair of electrons to the metal. So in total, how many electrons have been given? Total 3 electrons are donated by NO. So what is the donor ability of NO? NO plus. Total electrons given by NO plus. Important. Total electrons given by NO plus is 3. What is the shape? NO plus. Shape linear. This is linear. Very important. Very important. NO plus is linear and it donates 3 electrons. That is one way of satisfying the octet. Okay. That is one way of satisfying the octet. You can explain the same thing with MO diagram as well. I'm not taking that explanation now. We'll carry it afterwards. Now let's talk about NO minus. Let's say you have some metal. This is the case of NO 1, 2, 3, 1, 2, 3, 4. Okay, this was the case. So did you get over here? How did it satisfy the octet? It gave this electron to satisfy the octet. You see now it is satisfied. See, 1, 2, 3, 4, 5, 6, 7, 8. When nitrogen forms a triple bond, 6 electrons are satisfied from the bond and 2 electrons form the lone pair. So the octet of N is complete. Okay, now the other way to satisfy the octet of NO is it grabs 1 electron from metal. So metal becomes plus. It was like this. It has gained 1 extra electron. And now it is NO minus. NO now carries a minus charge. Okay, now the octet is complete. If the octet is complete, this lone pair of electrons can be now donated to the metal, this metal, to form the coordinate bond. So understand it very carefully. Now it carries a negative charge, okay? Understand it very carefully. This lone pair now is donated to the metal. So what is the total number of electrons given? So it was NO and then it has gained some electron and now it has become NO minus. When it is NO minus, the total number of electrons that it has donated is only 1. Correct? Out of the 2 electrons, 1 is already of the metal which it had occupied to complete the octet. Correct? So the 2 electrons, out of which 1 is of the metal, 1 is of the ligand. So the effective number of electrons given by the ligand is 1. And what is the geometry? Here, the metal and the ligand would form a linear geometry, but here the metal and the ligand would form a bent geometry. Why? Because this is sp2 hybridization. It needs an angle of 120 degree, and here it is sp hybridization. Here it needs an angle of 180 degree. Okay, so very important, NO plus donates 3 electrons effectively after completion of the octet, and it forms a linear geometry with the metal, while NO minus forms a bent geometry with the metal after its donation, and effectively it gives only 1 electron. Okay, so it has got a bent shape. Important. Now a few examples just for you to understand. See, let's say you have been given with a complex of Fe. You just note it down. Fe. This is sodium nitroprusside. This has been asked in the question. This is a P by Q. Sodium nitroprusside. You have to find the oxidation state. What is sodium nitroprusside? If you don't know the formula, you're gone. You have to know the formula. It is Na2 times FeCN 5 times NO. This is sodium nitroprusside. Okay. And you have to find the oxidation state of iron over here. Okay. So for that, let me explain. Sodium is plus 1. There are 2 sodium counter ions. So this is going to be plus 2. Iron, you don't know X. Cn exists as Cn minus, cyanide ion. So this is minus 1 into 5, minus 5. NO, you don't know whether it is linear or bent. It can be plus, it can be minus. If it is plus, it is linear. If it is bent, it is minus. Correct. So if you look at the structure, Fe, Cn, 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 5, right? Cn. Now, here you have the 6th one. I'll draw 2 possibilities. One is like this, NO, which is linear, and the other possibility is NO, which is bent. Okay, so here you can see the geometry is linear, 180 degree, and here if you see this is bent. But here when it 120 degree. So here if it is bent, you can see there is a lot of steric hindrance coming over here. But here they are straight. All the 6 ligands are linear and they are spacious. But here there is a lot of steric hindrance coming in, and this structure is not favorable. NO in its linear form is favorable, and hence here NO is plus 1. So what is the total oxidation state? Plus 2 plus X minus 5 plus 1 is equal to 0. Correct? Plus 2 minus 5 minus 3 plus 1 minus 2. Iron is in plus 2 oxidation state. This was a previous year question. Okay, so generally in octahedral complexes, because of the space limitations, they occupy or they have linear shapes most commonly. Okay, so this is about monodentate ligand. You have just one donor atom. So next one, bidentate. You might know the definition. Bidentate ligands. Bidentate ligands are those which have got 2 donor atoms. For example, oxalate. O minus. Two donor atoms. See? OO. So if this ligand is bound to a metal, how do you represent it? C O O C O O, and this is bound to the metal. See? Or simply what you would do is you will represent it like this. This is this is the representation of oxalate. What is the total charge of oxalate? 2 minus. Total charge of oxalate? 2 minus. Got it? This is oxalate. Oxalate. It is a symmetric ligand. You can call it a symmetric. Why do you call it a symmetric ligand? Because both the donor atoms are same. Symmetric. Another example is ethylene diamine. Very important. Ethylene diamine. CH2, NH2. You have got a lone pair over here. CH2, NH2. You have got a lone pair over here. This lone pair is donated to the metal to form the coordinate bond. Okay. Or else you can even notate it like this. Both of the donor atoms are the same, and hence this is also a symmetric ligand. What is the name? Ethylene diamine. Lot of questions, okay? Ethylene diamine, you represent it as En. Here you represent it as OX. When you solve a lot of questions, you will come to know about, you come to understand a lot about ligands. Okay, please do not sit and by heart the names of the ligands. It's going to take you ages. There are a lot of them. Okay, so these are the examples of symmetric ligands. Symmetric because both the donor atoms are the same. Now there are cases where the ligands are not the same. For example, glycine. Glycine. Glycine can be simply represented as NH2, CH2, CO, minus. Okay, so this lone pair of electrons from oxygen and this lone pair of electrons from nitrogen would donate. And how do you represent it? Simply like this. This can represent glycine. Okay. Now one which was asked in a question. So you represent, you write just like this, GLY. This is not symmetrical, asymmetrical. This is asymmetrical. Next is dimethyl glyoxine. Dimethyl glyoxine. This was asked in question. Dimethyl glyoxine, DMG. Okay, the structure is important. C double bond N OH. C double bond N O minus. Dimethyl. This is the structure of DMG. Who are the donors? This nitrogen and this nitrogen. They'll donate. Very important, okay? Don't get confused. N atoms are the donors. So this question has asked if DMG is mixed with nickel. If DMG is mixed with nickel, how many NiN bonds would be there? How many NiO bonds will be there? Etc. was asked. Okay. So the moment you mix this with nickel, the way it turns out to be is nitrogen, nitrogen. One OH is like this, one O is like this. Okay. C, please draw the diagram carefully. CH3, CH3. And then the lone pairs are donated to nickel, 2 plus. Okay. Similarly over here also, nitrogen. Here OH minus, here O minus, double bond C, double bond C, and then dimethyl. This is how it forms. Okay. Here there is no minus. So here nitrogens donate the lone pair of electrons. And this is a square planar structure wherein you can see the hydrogen bonds between this oxygen and this hydrogen. Similarly, this oxygen and this hydrogen as well. Square planar geometry. How many anion bonds are there? Nickel nitrogen bonds 4. How many nickel oxygen bonds are there? 0. This question was asked. So if you don't know the structure, again, so that's a problem with inorganic. You have to be familiar with the complexes. How do you generate this ligand? DMG. So usually what they do is if they ask in the questions, this would be the starting complex which is given. And then to this, they'll add NH3. So you can see here, both of them are in hydroxyl form. And once they add NH3, which is a very weak base will abstract only one proton and it becomes DMG, whose net charge is -1. Whose net charge is -1. Okay, clear, right? So that is about bidentate ligands. Bidentate ligands. So by now you know, what do you mean by tridentate ligands? It will have 3 donor atoms. What do you mean by hexadentate ligands? It will have 6 donor atoms. Okay, so you know that. So next you please write chelating ligands. Chelating ligands. So there are a lot of examples for bidentate ligands also. Okay, I've not written every one of them because you will get familiar. You will come to know about the different ligands once you start solving problems. Once you go into the deeper aspects of the chapter. Pyridine, you please write if you want. Pyridine. This is pyridine. This is bipyridine. Bipyridine, 2 nitrogen donors will donate electrons to the metal. Pyridine. Then you have phenanthrolene. Okay, there are many. There are many. Ah, hey, this is not phenanthrolene. This is anthracene. Sorry. Sorry. It's like this. Then from here you have the next one. And over here you have the third way. And these lone pairs. Okay. So this is phenanthrolene. This is bipyridine. This is donated to the metal and this becomes orthophenanthrolene. Okay. You just understand the concepts. So next one is chelating ligands. So chelating means they have the ability to form rings. Okay. So these are non-cyclic polydentate. Polydentate means more than 2 donors. Polydentate ligands that can form rings. That can form ring structures with the metal. Okay, no, polydentate means 2 can also happen. Okay, I said more than 2. No, it's not like that. Even 2 or more than 2. That can form ring structure on coordination with the metal. Okay, let me tell you one example. Let's say you have cobalt NH3 6 times. NH3 6 times. Let's say. So this is one structure where no ring formation has occurred. You have 6 nitrogen donors and you have cobalt ethylene diamine. We spoke about ethylene diamine, right? Like this. like this. Ethylene diamine. So here there is a ring structure, here there is no ring structure. And if they ask you to compare the stabilities, so if you can see in both the cases, the donor atoms are nitrogens. But the stability of the chelating ligands are always higher than that of the non-chelating ones. Stability of the chelating ligands are always higher than the non-chelating ones. Okay, so this is a typical example of a ligand which forms a ring. So can you see? See, there is a ring formed, a ring. So there are again many examples. Let's say diethylene triamine. So you have diethylene, that means 2-ethylene, NH, CH2, CH2, NH2, NH2. See, how many donors are there? 3. 1, 2, 3. All of these 3 can donate to the metal and they can form a ring structure. So this is diethylene triamine. Diethylene triamine. I hope you're understanding it, right? Correct. So next one, let's take EDTA. Very important example. EDTA. It's a hexadentate ligand. Hexadentate means it has 6 donors. Ethylene, diamine, tetraacetic acid. Okay, so you can see there are 4 oxygen donors and 2 nitrogen donors. Example of hexadentate ligand, example of a chelating ligand as well. Easy. Easy. Okay, so the next one, please write ambidentate ligands. Ambidentate. Ambidentate ligands are those where there would be 2 donors, but they are not bidentate. Let me explain. This is a good example of ambidentate ligand, and we wrote this example in monodentate ligand as well. So you can see here, sulfur has got 2 lone pairs of electrons, and it is SCN minus. So this will also get 1 extra electron, and this can also donate. Okay. So at a time, listen to my words, both S and N cannot donate at a time. Either S or N. Either S or N can act as a donor at a time. And that depends on the conditions. That depends on the conditions. So when you have a ligand where at a time only one atom acts as a donor, that is called ambidentate ligand. So write down at a time, a particular time, only one atom can donate the lone pair of electrons. So that actually depends on hard, soft interactions. We will learn about this in chemical bonding. Now, for the sake of understanding, just understand that sulfur is a soft center, nitrogen is a hard center. How did it become hard? How did it become soft? You will get it from chemical bonding. Okay, now soft centers will bind to soft metals only. For example, Ag+. Nitrogen won't bind to Ag+ because nitrogen is hard. Hard centers will bind to hard metals like cobalt 3+. So again, I repeat, how are these termed as soft or hard? You will get that understanding from chemical bonding. For now, just understand that if a metal comes and if it is soft, sulfur will donate. If a metal comes and it is detected to be hard, nitrogen will donate. Okay, that's it. So you have two different atoms, and at a time only one atom can donate. You might have two different donors, but then at a time only one can donate. So be careful. Let's say they ask SO3. Sulfur though does not have any lone pair of electrons. Here you have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Is this an ambidendate ligand? No. All are oxygens. You should need two different types of atoms, out of which only one will donate. You write it over here. Out of two different, very important. Out of two different atoms, out of two different atoms or donors, at a time only one atom can donate. At a time, only one atom can donate. Here, sulfur does not have any extra lone pairs of electrons. So SO3, all donors are O and it is not ambidendate. To call any ligand ambidendate, you should have at least two different centers and at a time only one will donate. Okay, so that is ambidendate. Easy. Next one is flexidentate. Flexidentate. Flexi. By the name flexi, you can understand it is flexible. Okay, you write certain examples. NO3 minus, this is being asked. CO3 2 minus, SO4 2 minus, PO4 3 minus, CH3 COO minus. These are all examples of flexidentate ligands. Flexidentate ligands means, let's say you take NO3. I'll take the example of NO3 because that was asked. NO3 minus. So you have got one minus. O. So this is 1, 2, 3, 4, 5, 6, 7, 8. Nitrogen can form only 3 bonds, but it is forming 4. So this will be plus. This oxygen will be minus to complete the octet. This will also be minus. So total charge is minus, NO3 minus. So if the atom is small, if the atom which is coming is very small, okay, there can be two possibilities. One possibility is when it comes in contact with a small metal, a metal which is in small sized metal. So what happens? Any one of the let me draw. Any one of the oxygen donors will donate the electrons to the metal and form a coordinate bond if it is small. Okay, this is what happens. But then if it is a big metal, so if it is a big metal, then what will happen? This is plus O, O, O. So it is big now. The incoming metal is big now. So this metal can come in contact over here and both of these will donate. So see how many donors are there? Two donors over here. So when you have a big metal, it is a bidentate ligand. But when you have a small metal, it is a monodentate ligand. So this is the meaning of flexidentate ligands. Flexidentate ligands are those where when you have a small metal, so you might think, why can't the small metal come over here and they can donate? No, that won't happen. If donation has to happen, these two bonds should come closer. So it will become like this. Okay. If these two come so close together, their angle, this is sp2 hybridized, it should be 120. That 120 angle cannot be attained if it forms a bidentate ligand with a small metal. Okay, that is not structurally possible. So if you have a small metal, it cannot fit over here. The two oxygen atoms cannot donate and shrink the angle. So it will act as a monodentate ligand, while over here it will act as a bidentate ligand. So this is the meaning of flexidentate ligands. Flexidentate ligands are those which can switch the number of donor atoms. The question which was asked was about ferric ammonium nitrate. Ferric ammonium nitrate coordination number was asked. Predict the coordination number of ferric ammonium nitrate. Ferric ammonium nitrate, you have to know the formula. NH4 twice. No. Formula was given. CeNO3 6 times. Okay. So understand that over here, coordination number was the question. Okay. Coordination number. What do you mean by coordination number? Coordination number is the number of donor atoms. Number of donor atoms. Be careful. I have seen many students, many lectures where they say it is the number of ligands. No, it's not the number of ligands. It is the number of donor atoms. For example, cobalt, ethylene, diamine, let's say. So this is basically 3 plus. CO, ethylene, diamine, 3 times 3 plus. So there are 3 ligands. What are the ligand number? Number of ligands, 3. What is the coordination number? Coordination number is 6. 6 donor atoms. 1, 2, 3, 4, 5, 6. So coordination number is the number of donor atoms and not the number of ligands. Okay. So it's the number of donor atoms. So understand that over here, NO3 is a flexidentate ligand. It can be monodentate or bidentate. Correct. So if it is cerium, so you can see it is with cerium. Cerium is a very big metal. So that will act as a bidentate ligand. So there are 6 NO3s. Each NO3 can, see, each NO3 has 2 oxygens which can donate electrons. So 6 into 2, 12 is the answer. 12. Okay, so there will be an option of 6, either because 6 number of ligands, or you might think NO3 is a monodentate ligand. It can turn into bidentate with big atoms. Okay, next, bridging ligands. Bridging ligands. Very easy. Bridging ligands means they can bridge, of course. So if they have to bridge 2 metals, you have 1 metal over here, you have 1 metal over here, and you have a ligand which has to bridge. So if it has to bridge, it should have 2 lone pairs. That's all. At least 2 lone pair of electrons are required. Okay, that's the condition for bridging ligands. For example, Cl minus. 3 lone pairs are there. H2, 2 lone pairs are there. SCN minus. SCN minus, see, sulfur, carbon, nitrogen with a negative, correct? This lone pair electron can go to a metal. This lone pair of electrons can go to a metal. It can bind like this. Or this lone pair of electrons can go to a metal. This lone pair of electrons from the same sulfur can go to the metal. Okay. Both of these are possible. Just understand that at least 2 lone pairs should be there to bridge 2 metals. Okay. Last is macrocyclic ligand. Last. Macrocyclic ligands are, as the name suggests, cyclic. So there'll be cyclic, macro. Macro means big, and there'll be polydentate as well. For example, crown ether. So I'll show you how does crown ether look. This is the ligand. 1, 2. Yeah, let me, okay, 1, 2, 3, 4, 5, 6. These are oxygen atoms, okay? They are connected like this. This is the ligand itself. This is the ligand. Okay. And you can see oxygen. Oxygen will have 2 lone pairs of electrons. These lone pair of electrons are donated to the central metal. So such big cyclic polydentate ligands are called macrocyclic. Examples, crown ethers, cryptans, porphyrins. Porphyrin ring and all you will learn in bioinorganic chemistry. Okay, so these are the different types of ligands, just the very basics of one of the component of coordination compound, which is ligand, okay? So revise the notes well. See you in the next. Bye.